Okay, so let's continue with our solid state PYQs. We will be learning about calculating the percentage efficiency of packing in case of SCC, which is we learned simple cubic cell. So now, how do we calculate the percentage packing efficiency of SCC? Okay, so there is a very simple formula. If you want to calculate the percentage packing efficiency of any of the following SCC, FCC, BCC, this formula is volume occupied by particles in unit cell divided by volume of unit cell, total volume, okay, remember total, into 100 because it's a percentage. So now by applying this formula, let me repeat: volume occupied by particles in a unit cell upon total volume of unit cell into 100. This gives the percentage packing efficiency. Now we are trying to find the percentage PE for SCC, which is simple cubic cell. Now there are few steps for this. The first step, so let's break down this formula. We need to first calculate the volume, then we need to calculate the volume of the unit cell. That's it. So for SCC, we have to calculate volume occupied by particles in the unit cell. So first we need to calculate volume of one particle. To calculate volume of one particle, we know that it's a sphere. So let's write step 1, radius of sphere. We have to calculate this. Now to understand how to calculate radius of sphere, we need to understand the diagram of SCC. Yes. So now in simple cubic unit cell, this is a simple cubic unit cell, the particles are at the corners and they touch each other along the edge. So what does this mean is, this is not the correct structure. To make the correct structure, this is very important because they touch each other along the edge. This line is very important. So we come to know from this that these atoms are so big and they are touching each other along the edge like this. You get the point, right? These atoms, they touch each other, they are so big. So now we need to find the radius of sphere. So if we consider one atom like this, it will have radius. Now let's take this atom as this one. As this one. So this has a radius and this has the radius. They both are same. My drawing does not look same, but it's the same radius. So the two radiuses make one side of the cube. Okay, and we can also consider the side of a cube as A. We can write it as A So therefore we get the equation 2r is equal to a, or or r is equal to a by 2. Now we get this relation for SCC. Now we go to the second step, which is step 2. Step 2 is considering volume of sphere. Why did we calculate the radius? Because what is the volume of sphere? It is 4 by 3 pi r cube. We didn't know this r, so to know this r we need to calculate it first. Now we'll calculate, as we know already the value of r, we will just calculate it now, and we replace r by a by 2 the whole cube. So now we get, if you want you can expand this, it will become 4 by 3 pi into a cube by 8, as 2 cube is 8. Cancel this, you get pi by 6 into a cube pi by 6, or pi a cube by 6, whatever you like. Now we have found the volume of occupied by particles in unit cell. Okay, before that there is a important thing to understand. This pi a cube by 6 is the volume of one unit cell. Okay, now in SCC, as we saw, there are only 8 atoms, and as we saw last time, they are being shared with other 7 neighboring atoms. So in total only one atom, all these atoms just make up one atom, because only like 1/8 part is getting saved in each corner, multiplied by 8 corners. So only one whole atom is being formed by these 8 small atoms. Okay, that's why this remains same for all the particles in the unit cell. This is only for one particle, but it remains same in case of SCC for all the particles in the unit cell. So we got the numerator, this. Now we need the denominator, total volume of unit cell. So how do you get the volume of the unit cell? If you are considering this as a cell, it's a cubic structure. How do you get volume of cube? We'll write it down. Now next we need step 4, volume of unit cell. Volume of cube is side cube, which is a cube. Now we can just put these values into this equation. Volume occupied by particles. So let's write here, total percentage packing efficiency for SCC is volume occupied by particles in a unit cell by 6 divided by total volume of unit cell, which is a cube, into 100. You simplify this, pi a cube by 6 into inverse of a cube into 100. Cancel this, so you get pi by 6 into 100. As you simplify this, you can write this as 3.14 into 100 by 6. Also, you can change the decimal point, remove the decimal point. Now divide this. 6 5s are 30. 1 4 6 2s are 12. 2 remainder, you add a 0. 6 3s are 18. It's 52.3%. This is the percentage packing efficiency of SCC, which is simple cubic structure. So what does packing efficiency actually signify? It just means how much of this is, like, how much space is being occupied by these atoms or particles, you can say. Packing efficiency, like just like how in a bus, suppose there are 24 seats and only 21 are full, so then you can understand that how full is the bus by looking and see that 3 seats are left. So the same way we can say from percentage packing efficiency that only 52.3% of the whole cube is full with particles. The rest is empty. How to know the rest? You just minus by 100. Minus 52.3, 0, 7, 7, 47.7% is empty. So this was percentage packing efficiency of SCC, which is simple cubic cell. We can also calculate the same for other. We can also calculate the same for FCC. Okay, let's try. Let's first make a model. FCC looks like this. And each face has one particle or atom. Okay. Now, as in the last class we had learned that how many atoms does an FCC molecule have? It was 4. How? These side atoms are shared with other 7 neighboring atoms, and as we learned, even in SCC they make up one whole atom. So 1 plus, now to these there are 6 faces, and each of these side face atoms are shared with one more of the cube, one side of one more cube. So half atom from each side into 6 faces. This becomes 2 3 2. I'm sorry, cancel 3, and 3 plus 1 4. So we know that there are 4 atoms or particles in FCC. Now if you want to calculate the percentage packing efficiency, let's write down the formula, which is volume of particles in unit cell upon total volume of unit cell into 100, as it's a percentage. Okay, now let's again start with the steps. Step 1, is finding the radius. Find radius. I'll do it again, but the actual radius is the, what do you call that, the relation between radius and edge length is r is equal to a by 2, or a is equal to 2r. This is the radius and edge length comparison, or you can say, I forget the word. Okay, let's continue. Now we want to find the volume. So then yes, volume of sphere is 4 by 3 pi r cube. Now here things become a little different, because if you see the model of FCC again, it can look like, suppose this is a molecule, this is a molecule, and the middle molecule, if I make it down, looks like this. So there are four radiuses which make up one edge length. Okay, so there are four radiuses which make up one edge length. So these two relations are totally wrong. So we need to find a new relation. Okay, so now we know that 4r is equal to a, or a is equal to, r is equal to a by 4. This is the actual relation for FCC. Remember, FCC. So now applying this in this formula, we get we get 4 by 3 pi. Instead of r cube, we write a by 4 the whole cube. We can simplify this as 4 by 3 pi a cube by 4 cube. You can cancel this 1 4 by this and make it 2. So we get pi a cube by 4 square 16, 16 to 32, 16 3s are 48. Let me see online if this is true or no. Give me a minute. Packing efficiency of FCC. Okay, so we have gone wrong in the diagram. We can't bring this thing down from between. So we need to make a new diagram now. Give me a minute. Okay. So the actual diagram will look like this is in between, this is on the side, and this is on the side. So we have to consider this diagonal, not the edge length. This is how we'll get the relation between edge length and radius. This can't shift down, so there are we will still get 1 2 3 4 5 sorry 1 2 3 4 4 hours here. Now but by geometry we know that this diagonal is equal to, so let's write face dia face diagonal is equal to root 2 of A. And how do you prove this? Because so this is given by Pythagorean theorem. We know that this is A and this becomes a right angle triangle as it's a cube. So we will get this as, if suppose we consider this FD, face diagonal square, is equal to A square plus A square. So we write FD as 2A square. Now you have to put under root, so FD becomes root 2A. This is Pythagoras. So this face diagonal is root 2A, and then now We know that phase diagonal is 4r, so we write it 4r is equal to root 2a this is the actual relation, and we get r as root 2a by 4. We can also write 4 as root 2a by okay, suppose you want to a by 4. Okay, now you want to consider a. So a will be 4r by root 2. How do you simplify this? So 4r by root 2. Simplify this. Okay, you multiply both sides by root 2. So you write 4 root 2 r upon root 2 into root 2. So this will become 2. So then you cancel 1. No, you don't cancel it. Root 2. It is equal to 2. So 2 root 2 r. Called rationalization. Fine. This, so you get this as the relation between a and r. Finally, you have reached the destination. Now for the next step, we want to find volume of sphere, which is 4 by 3 pi r cube. pi r cube. So now you substitute this instead of, okay, first you find r. So r becomes a by 2 root 2. This will become 4 by 3 pi into a by 2 root 2 the whole cube. Then so you can write this as 4 by 3 pi into a cube by 2 cube 8 into 2 is 2 and 2 root 2 4 root 2. So this will be pi a cube by 4 to 4 12 root 2. But this is the relation, no? So one why were we substituting here? We're substituting अच्छा हाँ one only particle is there. Okay, this is all wrong. You don't need to substitute this. Okay, so as we know that, so in SCC, after we calculated the volume occupied by atoms in the unit cell, we did not multiply it by anything because there was only one atom. Now as we know here that there are 4 atoms in FCC. Okay, so now we need to multiply that volume by 4. So now let's write here. So we know that volume has to be 4 by 3 pi r cube. Okay, so now you just multiply this by 4. And you don't need to, like, what do you call that, substitute this in this. Just write 16 by 3 pi r cube. This is the volume, and we know that the volume of total unit cell, total volume of unit cell is a cube. Okay, so this will be equal to, okay, what was A? A was 2 root 2 r, the whole cube. So this will be 2 cube 8 into 2 root 2 r cube. So 16 root 2 r cube. So this is total volume of unit cell. Now you just put these two values in the original equation. So the total percentage packing efficiency formula, total volume of all the particles in the unit cell, which is this. So you write 16 by 3 pi r cube, and then you divide it by 16 root 2 r cube. This total is multiplied by 100 as it's a percentage. From here you can understand r cube will cancel because it's divided. 16 will cancel. So now what is left is pi by 3 divided by root 2 into 100. So you simplify this more. Pi by 3 root 2 into 100. 3 root 2 into 100, which approximately comes out to be 74%, 0.05%. This means that 74% of volume is occupied by atoms and the remaining is empty space in this. This high packing efficiency is why FCC structures, these are common in metals like aluminum, gold and copper. So FCC structure is common in atoms not atoms, metals like copper, gold, aluminum. This structure, it has high packing efficiency. Okay, now let's try for BCC. This structure will look like there is one single in the body. So then we come to know that total number of atoms in BCC is equal to, we know that this all 8 corners make 1 plus 1, which is equal to 2. So the total number of atoms in BCC are 2. Now let's calculate percentage packing efficiency. Okay. Volume of particles in unit cell, okay, divided by total volume of unit cell into 100. Okay, so now we will calculate the relation between radius of sphere and edge length of cube. So that will be, now is the tricky part. So we need to consider this, like we need to consider the cross diagonal length. So how do you do that? It's already done here. Mm. So now let's figure out body diagonal equals 4r. So now to understand how to calculate body diagonal, this is called body diagonal, this was face diagonal, and this is edge length. So to calculate body diagonal, we need to see in 3D. Now consider the cube in 3 dimensions. Body diagonal forms a right triangle, okay, with one edge of the cube, which is this, and the face what do you call that, diagonal, this. Okay, so according to Pythagoras theorem, the body diagonal will be, let's draw it properly. Suppose this is the cube, and suppose this is body diagonal. This will be considered edge length, and this will be face diagonal, and this forms a right angle triangle. So now by Pythagoras theorem, body diagonal square will be equal to face diagonal square plus edge length square. Now, so to calculate this, we can also write it as, and now when you root it, now from previous this thing we also knew that face diagonal is equal to root 2a. Okay, so you can also write this as BD is equal to root 2a the whole square plus a square. Okay, so BD will be root 3a square, which will equal to root 3a. So we came to know that body diagonal is root 3a, just like face diagonal was root 2a. Okay, so we got that body diagonal is root 3a. Now we knew that body diagonal was 4r, so we get 4r is equal to root 3a. From here we get r is equal to root 3 by 4a. Okay, now we consider the volume of the sphere. So that is 4 by 3 pi r cube, and as there are 2 atoms, we multiply this by 2, so it becomes 8 by 3 pi r cube. Now we see total volume of unit cell, which is a cube. A cube will stay as so we know that equal to a cube. So how do you simplify this? We can take the value of a from this equation, this equation, and get a is equal to 4 by root 3 r. 4 by root 3 the whole cube. So come out with 4 cube 64 r cube by 3 root 3. Now you just divide these. So 8 by 3 pi r cube divided by 64 r cube by 3 root 3 into 100, because it's a percentage. From here you can clearly understand r cube will be gone, 3 will be gone, 8 and here 8. So what we get is pi divided by 8 by root 3. So we can also write this as 8 by root 3 pi into 100. We need to remember mathematics, always it becomes pi into root 3 by 8, not the other way around. So this is not valid, into 100. So this will be around 68%. Okay, so now we have calculated the packing efficiency of all three crystal structures. So let's write once again SCC, FCC and BCC. So the packing efficiency of BCC we have seen is 68% and that of FCC was 74.05%, and now of SCC was 52.36%. We need to remember these values, very important. This is the derivation. Now we come to our next topic, which is crystal defects and imperfections. So now there are we will be studying point defects. So basically in all the crystal defects there are a few defects. One is point defect. This point defect, first one. Second one is line defect, which we are not going to study. Third one is surface defects. Here we are only going to study point defects. In point defect there are 5 defects. Also you can classify them as vacancy defect. Okay. Second one is interstitial defect. Third one is substitutional defect. Then come two most important, Schottky defect and Frankel defect. So these are point defects. They only apply on each point of atoms. Okay. Now let's start with vacancy defect. A vacancy is a point defect where an atom is missing from lattice site. So you can understand if let's start. Let's consider vacancy. Okay. So if these are the atoms, suddenly there will be an atom missing, or more than one atom missing. That will be called a vacancy defect. One or few atoms are missing. This is called vacancy defect. The name says it all. Then comes the interstitial defect. Okay. So in this case, an extra atom occupies a space between the regular lattice positions. Now suppose this is there. Okay. This is a regular lattice position, and that an extra atom, somewhere it has come, or one or more atoms, and they have installed themselves in between. This is interstitial. Interstitial means in between. This is the English meaning of interstitial, in between. Right, interstitial means in between. Now comes substitutional defect. Here an atom in the lattice is replaced by a different type of atom. So what happens is this, suppose this is the lattice. I'll use the eraser to wipe these off. Okay. Suppose this atom just suddenly becomes gayab, ceases to exist. It is replaced by another atom, which is this. It's a different atom. It's replaced. Actually, even this atom is replaced by this atom, the new atom. This is called substitute. This is being substituted. I think the name specifies the characteristics of the defects. First we saw vacancy, where the atom itself disappears. Then comes interstitial, in between. An atom suddenly lodges in between the original lattice site. Now comes substitutional defect, where the atom substitutes puts itself in another atom's place. Now the last two important defects are Schottky and Frenkel defect. So Schottky defect involves a simultaneous absence of an equal number of cations and anions from the lattice sites. So suppose there was an ionic crystal here. Suppose there were plus, sorry, suppose there were plus, minus, 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 plus. This was a lattice site. Okay. Now, suddenly, I tell you, in pairs, okay, equal number of cations and anions are missing. So this plus is missing and this minus is missing. This is a Schottky defect. Suppose more pairs also can go missing. Suppose this plus is missing and this minus is missing. This is also be considered as Schottky defect. Suppose this plus is missing, this minus. This is also a Schottky defect. But it has always to go in pair. If only this is missing and there are no equal number of minus in pairs missing, then it won't be considered as Schottky defect. Now we come to Frenkel defect. This is remember the Schottky defect is only typically occurs in ionic crystals, as these are ions. Now suppose this can also be in so suppose this was plus 2 charge, so 2 plus charge, this was 3 plus charge, 4 plus, so it will all balance each other out. And suppose here plus 2 have gone, suppose I removed 4 minus charge, then these 2 plus 2's have to go together, then only it will balance itself out. This is Schottky. You write it as SCHOTTKY, Schottky defect. Now let's come to Frenkel defect. This defect involves an atom being displaced from its normal lattice site to an interstitial site. It results in vacancy and an interstitial defect. So this is like vacancy and interstitial. Let's take this example. Suppose there was an atom here before. It was a full set, okay. And then suddenly this atom decides to go and sit here. And this atom decides to go and sit here. So this created a vacancy defect and also an interstitial defect, as you can see. But they are the same atoms. Atoms did not change. So this is known as Frenkel defect. Okay, this is Frenkel defect. Now there are a few questions in the PYQs which are based on this topic. This was just a basic explanation. Now we will do the questions. So there's a basic question which comes: what are Schottky defect and Frenkel defect, and how do you write it? So I'll just explain them to you. We'll write them together. This was asked in 2013. Okay. What are Schottky and Frenkel defects? What are Schottky and Frenkel defects? Answer: Schottky defect is formed in an ionic solid. Schottky defect is formed in an ionic solid. Okay. When equal number of cations and anions are missing. Okay, from their regular positions in the crystal lattice, thus creating vacancies. Okay, this is Schottky defect. So this defect is usually found in ionic crystals. Examples like NaCl is an ionic crystal, AgBr and KCl. These are ionic crystals that are Schottky and Frenkel. So now we have to explain Frenkel defect. Frenkel defect arises when an ion of an ionic compound is missing from its regular lattice.
1 by